morning, students. This is lecture number 13. The title is Case Studies and Exercises Part 2. In this lecture, we will study some exercises based on the graphical solution of an LPP. Then we will study some problems on the simplex method of solution of an LPP, and then we will study the two-phase method for the solution of an LPP. Now, exercise 5 is as follows. We are required to solve graphically the linear programming problem given by minimize f is equal to minus 4x1 plus x2 subject to x1 minus 2x2 less than or equal to 2 and minus 2x1 plus x2 less than or equal to 2, where x1 and x2 are less than or equal to 0. You will observe that in general, in most of the LPs, the x1 and x2 are supposed to be greater than or equal to 0, but in this interesting example, the restriction is given to be that x1 and x2 have to be less than or equal to 0. However, in the second part of the problem, we are also required to solve the problem when x1 and x2 are greater than or equal to 0. So, the first part has the solution given by 0 comma minus 1 with f is equal to minus 1, and the second part of the problem has a solution 2 comma 0 with f is equal to minus 8. Now, let us try to solve this problem with the help of the graphical method. So, the given problem is minimize f is equal to minus 4x1 plus x2 subject to x1 minus 2x2 is less than or equal to 2 minus 2x1 plus x2 is less than or equal to 2, x1 and x2 are both less than or equal to 0. So, the first line has to be plotted using these points. X1 is equal to 0, x2 is equal to minus 1, x2 is equal to 0 and x1 is equal to 2. Similarly, the second line has to be plotted using 0 comma 2 and minus 1 comma 0. This is the way that has to be done as I have explained earlier. Now, let us plot both these lines 1, 2, this is the origin, minus 1, minus 2, 1, 2, minus 1, minus 2. Now, the first line has to be plotted, that is 0 comma minus 1. So, 0 comma minus 1 is here. I will call this point, let us say A, 0 comma minus 1, and the second point is 2 comma 0. So, this is the point 2 comma 0. First line has to be and in order to see which side of the line is the feasible region, we will substitute the origin and we find that the feasible region is above the line. Also, the second line has to be plotted using 0 comma 2, which is the point 0 comma 2, this one is the point, and minus 1 comma 0, this one is the point. So, therefore, we will join these two points and what do we find? We find that the feasible region is below this line. So, this is the feasible region below the line. Also, since x1 and x2 are less than or equal to 0, therefore, the feasible region looks as follows: A given by 0 comma minus 1, B given by minus 2 comma minus 2, and C given by, this is the point C. So, therefore, we have the feasible region as follows. Please note, the special nature of this problem is that the x1 and x2 have to be less than or equal to 0. So, now comes the time to find out what is the value of the objective function at each of these points. So, therefore, at the origin we need to find out what is the objective function value. The objective function is minus 4 x1 plus x2, and at the origin the objective function value is 0. Then comes the second point A given by 0 comma minus 1, objective function comes out to be minus 1. Then comes the third point, that is B is the point minus 2 comma minus 2, its objective function value is 6, and the third point is C minus 1 comma 0, its objective function value is 4. And what do you find? The minimum occurs at the point A, and this is the solution to the problem. So, I hope everybody has understood how the third quadrant is the feasible region. The second part of the question says that we have to find out what happens when this x1 x2 has to be greater than or equal to 0. In this case, the feasible region is the first quadrant. So, this is the feasible region, please make sure you understand how the feasible region has to be plotted. And in the second part of this feasible region of this question, the points that have to be considered are as follows: P, origin and Q. P is given by 0 comma 2 and Q is given by 2 comma 0, and of course, the origin is as it is. So, in this case the objective function value is as follows: for 0 comma 2 it is 2, and for 2 comma 0 it is minus 8, and at the origin it is 0. Since we want to minimize the objective function, of course objective function is the same as before, there is no change in that. The solution to this second part of the problem is at the point Q given by 2 comma 0, because the objective function value is minus 8. So, I hope you understand how the x1 x2 whether it is less than 0 and whether it is greater than 0, how it helps in designing the problem in a new way. Let us look at exercise number 6. In this problem, we have to solve the given LP using the two-phase method, and we have to prove that this problem has no feasible solution, and also we have to verify graphically that this problem has no feasible solution. The problem is minimize 3x1 plus 2x2 subject to the condition 2x1 plus x2 is equal to 0, 3x1 plus 4x2 is greater than or equal to 12, x1 and x2 are greater than or equal to 0. The interesting thing to note in this problem is that the first constraint is in the form of an equality. It is neither greater than nor less than. So, this indicates the problem complexity, how to design the feasible region which is consisting of a line segment. So, let us try to solve this problem first with the graphical method and then with the two phase method. So, the problem is minimize z is equal to 3x1 plus 2x2 subject to 2x1 plus x2 is equal to 2, 3x1 plus 4x2 is greater than or equal to 12, and as before we will write x1 and x2. If x1 is 0, then x2 is 2 and the second point is 1 comma 0, and for the second constraint if x1 is 0, then x2 is 3 and the second point is 4 comma 0. So, therefore, let us plot the problem like this. We need to do the demarcation. And the first constraint means the line should pass through 0 comma 2 this point and 1 comma 0 this point. So, here is the 0 comma 2 and 1 comma 0. So, the feasible, since this is a equality constraint, there is no greater than or less than. So, we are concerned with this line segment. Then comes the second constraint 3x1 plus 4x2 greater than or equal to 12. This passes through 0 comma 3 and 4 comma 0. And as you can see that since this is a greater than or equal to constraint, so therefore 0 is greater than or equal to 12 is false. So, therefore, we need to evaluate the objective function at the 2 points A given by 0 comma 2 and the point B given by 1 comma 0. The objective function is given to be 3x1 plus 2x2 which comes out to be 4 and 3. Since this is a greater than or equal to constraint, that means that the feasible region is above the line, and since the second constraint is this line segment A and B, but we need to find out the feasible region, and because one constraint shows that the feasible region is above the line and the second constraint shows that it is the line segment. So, therefore, there is no feasible region, and that is what is the solution to the problem if you solve it graphically. Now, we have to verify that this has to be solved with the help of the two-phase method. So, let us try to solve it using the two-phase method. In the two-phase method, we need to write down the constraints and the objective function in the standard form. So, the given problem minimize z is equal to 3x1 plus 2x2 has to be converted into the maximization type by multiplying with the negative sign, and the constraints, that is 2x1 plus x2 is equal to 2. Similarly, 3x1 plus 4x2 is equal to, because now this is greater than, so for greater than we need to subtract a surplus variable and make it an equality. However, remember, we need to find a BFS for both the equations. So, therefore, we will add an artificial variable in the first equation and similarly an artificial variable in the second equation, because these are the basic variables. So, therefore, our two-phase method will begin like this. We have to minimize A1 plus A2 subject to these constraints, right. Remember, in the two-phase method, the first phase, phase 1 is nothing but minimize the sum of the artificial variables, and here we have A1 as an artificial variable in the first constraint. Similarly, A2 is a artificial variable in the second constraint. So, therefore, in the first phase we will set aside the given objective function and minimize the sum of the artificial variables. So, now we are ready to solve this again with the help of the phase 1. So, let us write the basis. Now, the basis is A1 and A2 and the variables are x1, x2, x3, A1, A2 and the right hand side. So, we can translate the given data as follows: 2 3 1 4 0 minus 1 1 0 0 1 and the right hand side is 2 12. Also, we need to write the coefficients of the objective function. Since we are working with the phase 1 means that our objective function is minimization of A1 plus A2, and in order to bring it to the standard form we have to maximize minus A1 minus A2. So, that means the coefficient of A1 is minus 1 and similarly the coefficient of A2 is also minus 1, whereas the coefficients of x1, x2, x3 are 0. Over here on the left hand side we need to repeat the coefficients of A1 and A2 as minus 1 and minus 1. Next, we need to calculate the deviation entries. So, what are the deviation entries? They are obtained like this: 0 minus 1 multiplied by 2 3, and using this the deviation entries are 5 5 minus 1 0 and 0. Remember that the deviation entries corresponding to the basic variables is always 0. Next, we perform the test for the incoming variable, and in the incoming variable we find that x1 is taken to be the incoming variable, although you can choose between x1 and x2,
the iterations will vary, but finally the solution will be the same. And the minimum ratio test tells us we have to find out the minimum of 2 by 2 and 12 by 3. So, the right hand side divided by the pivot column, which tells us that the first entry is the minimum, and this indicates that 2 is our pivot, and therefore, we have to make this as 1 0 in the next iteration. A1 will go, so it will be replaced by x1, A2 will be as it is, and in this iteration we have 1 by 2. Of course, you need to apply the elementary row operations, that is R1 has to be replaced by 1 by 2 R1 and R2 has to be replaced by R2 minus 3 R1, and using this you get the new iteration as follows: 1 1 by 2 0 1 by 2 0 1, and the second row will become 0 5 by 2 minus 1 minus 3 by 2 1 and 9. Again we need to find out the deviation entries, and they turn out to be 0 5 by 2 minus 1 minus 5 by 2 and 0. This is obtained by the normal procedure in which, just as I have explained over here. Now we find that there is only one entry in the deviation row which is positive. This indicates that x2 should enter into the basis. Then we perform the minimum ratio test between the right hand side and the pivot column, which tells us that it is 1 upon 1 by 2 and 9 upon 5 by 2, and this tells us that the pivot is 1 by 2. Therefore, the next iteration has to be implemented and we get the new basis as, this is x1 and x2, and this tells us this is x2 and this is A2, and this tells us that we have to apply the elementary row operations as R1 times 2 R1, which gives me 2 1 0 1 0 2, and the second row, the elementary row operation has to be R2 has to be replaced by R2 minus 5 by 2 R1, which gives me minus 5 0 minus 1 minus 4 1 and 4. Again we calculate the deviation entries and we find that the deviations are minus 5 0 minus 1 minus 5 and 0. So, what do we find? We find that all the entries in the deviation row are either 0 or less than equal to 0. This means that the stopping criteria has been satisfied. The stopping criteria is satisfied. However, we find that A2 is still there in the basis, because this BFS is A2 is equal to 4, x2 is equal to 2 and all other 0. But remember, what was our A2? A2 was a artificial variable, and since it is an artificial variable, but it has still not been removed from the basis, it indicates that the problem has no solution, because artificial variable is still in the basis. So, I hope you remember that this is the condition where we had specified that if the artificial variable is still in the basis, but the stopping criteria has been satisfied, therefore, this is an indication that the problem has no feasible solution. So, now let us come to the exercise number 7. Solve by the two-phase method the minimization of z is equal to 3x1 plus 2x2 plus x3 subject to x1 plus x2 plus x3 is equal to 4 and 2x1 plus 5x2 minus 2x3 is equal to 3. The solution to the problem is 11 by 4, 0, 5 by 4 and z is equal to 19 by 2. So, let us solve this again using the two-phase method. Now, as you know that the two-phase method means that we need to convert the problem first in the phase 1. In the phase 1 we need to write the problem in the following manner: maximize z is equal to 3x1 plus 2x2 plus x3 subject to x1 plus x2 plus x3 is equal to 4, 2x1 plus 5x2 minus 2x3 is equal to 3, and we need to add artificial variables in the first equation and another artificial variable in the second equation. So, the basis is A1 and A2 and therefore, that is what we will write. So, here is the basis. A1 and A2 is the basis, and we need to write the objective function as in the phase 1 it has to be maximization of minus A1 minus A2, because remember the artificial variables have to be minimized, and this becomes x1, x2, x3, A1, A2 and the right hand side. So, we will write down the entries, that is 1 2, 1 5, 1 minus 2, 1 0, 0 1 and 4 3. And the coefficients of the objective function are only minus 1 and 1, minus 1 for A1 and A2 and the remaining as 0. Again we need to write down minus 1 and minus 1 again for the coefficients of the basic variables. Then we need to calculate the deviation entries, which comes out to be 3, 6, minus 1, 0 and 0. And you can see that 6 is the largest, and according to the minimum ratio test 5 becomes the pivot. So, we need to apply the elementary row operations accordingly, and our new basis will become A1 and x2. And the new table that you get is 3 by 5, 0, 7 by 5, 1, minus 1 by 5 and 17 by 5. Similarly, the second line becomes 2 by 5, 1, minus 2 by 5, 0, 1 by 5 and 3 by 5. then the deviation row becomes 8 by 5, 0, 7 by 5, 0 and minus 6 by 5. Here again we find that the pivot is 7 by 5 and therefore, we apply the elementary row operations as before and we get x3 and x2 as the basis. This gives the new table as the first row is 3 by 7, 0, 1, 5 by 7, minus 1 by 7, 17 by 7 and the second row becomes 4 by 7, 1, 0, 2 by 5, 1 by 7 and 11 by 7 and the deviation row becomes 0, 0, 0, minus 1, minus 1. Now, what does this show us? This shows that the stopping criteria is satisfied and since the stopping criteria is satisfied, therefore, the phase 1 has been completed. So, phase 1 is complete. Now, using this BFS, we can start the phase 2 and in the phase 2, we will use the same basis and at the same time we can forget about the A1 and the A2 and the simplified table looks like this. So, now we are left with x1, x2 and x3 and we need not write A1 and A2 because already they have been removed from the basis. So, we will write the right hand side and the corresponding value of x1, x2 in the objective function will be 3, 2 and 1. The basis is x3 and x2 and this turns out to be the same table will come over here 3 by 7, 0, 1 and 4 by 7, 1 and 0. Remember that A1 and A2 have been deleted. So, these two columns have been removed. Right hand side is 17 by 7 and 11 by 7. Then comes the deviation entries. Now, the deviation entries will be different. They will be different from the ones given over here in the phase 1 because now the objective function have changed because in the phase 2 remember bring back the original objective function. So, now we have the deviation entries as follows 10 by 7, 0 and 0. Remember that the deviation entries corresponding to the basic variables are 0. Similarly, we will apply the test for the outgoing and the incoming and this is the pivot and the new iteration will become the basis will be x3 and x1 and what do you find? You find 0 comma 1 minus 3 by 4, 7 by 4, 1 0 and right hand side is 5 by 4 and 11 by 4 and the deviation entries are this you find are all less than or equal to 0. So, this means that the stopping criteria has been satisfied and this is the solution. So, what is the solution? Solution is 11 by 4, 0 and 5 by 4. Hence the proof. So, with this we come to an end of the
second part of this examples and case studies. Thank you so much.